Welcome to the Hearing Machine, the complete visual guide to modern speech AI. In this video you will learn the complete pipeline, from raw sound waves all the way to a full voice assistant. Mel Spectrograms, turning raw audio into a 2D fingerprint. Transformers, the global attention mechanism that powers modern AI. Conformers, combining global attention with local convolution. CTC versus transducer, aligning audio frames to output words. The full voice pipeline, from microphone signal to spoken response. These concepts live inside every voice product in the world. Understanding them means understanding modern AI at its core. Let us start from zero and build the full picture. Sound is a continuous pressure wave. A microphone digitizes it at 16,000 samples per second for speech systems. We slice the signal into short overlapping windows, 25 milliseconds each, stepping forward 10 milliseconds at a time, giving 100 frames per second. Each window is multiplied by a Hamming function, a smooth bell curve tapering to zero at both edges. Without it, sharp boundaries smear energy across frequencies. Spectral leakage. Applying the fast Fourier transform to each windowed frame gives its power spectrum, the exact energy at every frequency. We apply a Mel filter bank. Triangular filters spaced on the Mel scale. At low frequencies they are narrow and closely packed. At high frequencies they widen. This matches human pitch perception. The Mel formula is logarithmic, matching human pitch sensitivity. Below 1 kHz, filters are narrow for fine pitch detail. Above 1 kHz they spread, just like our ears. Each audio frame produces a vector of Mel filter energies, typically 80 values. One column. Stack hundreds of those columns over time and you get a two-dimensional heat map, the Mel spectrogram. The horizontal axis is time. The vertical axis is Mel frequency. Each cell's color shows the energy. Bright means loud. Dark means quiet. We take the logarithm of each energy value. A loud sound can be a billion times stronger than a quiet one. The log step collapses that range into values a neural network can handle. MFCCs add a discrete cosine transform on top of the log Mel spectrogram. This was needed for old Gaussian mixture models requiring uncorrelated inputs. Modern neural networks handle correlated features naturally. So we skip the DCT and feed raw log Mel directly. The transformer's core power is self-attention. Every position can look at every other position simultaneously, not just its neighbors. Here, key computes attention against every other token. Thicker lines mean higher attention weight. It attends most to itself and to contextually related words. Every input is projected into three roles. Query asks, "What am I looking for?" Key says, "This is what I contain." Value says, "This is what I will contribute." We dot product query and key. Scale by root decay to prevent saturation. Then apply softmax to get attention weights. The output for each position is a weighted sum of the values, where the weights are the attention scores we just computed. A full transformer block. Layer norm. Multi-head attention. Residual add. Then another layer norm. Feed-forward network. Residual add. The residual connections. Adding the original input back. Allow dozens of blocks to stack without losing signal. The transformer excels at global context, linking distant sounds. CNNs are expert at local patterns, the shape of a consonant or formant. The conformer combines both in a single block, achieving state-of-the-art ASR. The first feed-forward module uses only half its output, the Macaron half-step arrangement that stabilizes training. Multi-head self-attention uses relative positional encoding, making it robust to variable utterance lengths. The convolution module. This is what separates the conformer from a plain transformer. It scans locally across time. A second identical half-step feed-forward mirrors the first, completing the symmetric Macaron structure. A final layer normalization stabilizes the block output. Inside the convolution module. Pointwise expansion. GLU gating. One-dimensional depthwise convolution across time. This is what gives the conformer its local acoustic sensitivity. Batch norm and swish follow, then projecting back to the original dimension. Connectionist temporal classification extends the output vocabulary with one special symbol: blank. At every acoustic frame, the model predicts either a real character or blank, meaning nothing to output right now. Here is a typical raw output for the word hello. 3 H frames, then blanks, 1 E, blanks, multiple L frames, and so on. First, collapse any consecutive run of identical labels into one. 3 H frames become 1 H. 2 L frames become 1 L. Second, remove all blank symbols. What remains is the clean decoded text, hello. CTC's critical weakness. Each frame is predicted independently. There is no internal language model. 4 apples and 4 apples sound identical. CTC cannot distinguish them. An external language model must be added during beam search to fix this. The transducer solves CTC's context problem by adding a predictor network, an auto-regressive model conditioned on all previously emitted tokens. This gives the system an internal language model. The architecture has 3 parts. The encoder processes audio and produces a vector per frame, FT. The predictor processes all previous output tokens and produces GU. The joint network fuses both and predicts the next symbol. Decoding moves through a 2-dimensional lattice. Moving right consumes one audio frame, blank. Moving up emits a token without consuming a new frame. Unlike CTC, the transducer can emit multiple tokens per frame, moving up several steps before consuming the next audio frame. Because the predictor conditions on all past output, the system is its own language model. Quick comparison. CTC is fastest but needs an external language model. The transducer streams natively with built-in language context, the industry standard for live voice assistants. Attention encoder-decoder achieves the highest offline accuracy but requires the full audio before emitting any text. Voice activity detection runs continuously with minimal power, forwarding audio only when actual speech is detected. A tiny wake word model, sometimes under 100,000 parameters, listens for the trigger phrase before waking the full system. A conformer encoder and transducer decoder convert the incoming audio to text in real time, streaming word by word as you speak. Natural language understanding extracts intent and entity slots. The dialogue manager tracks conversation state and calls any needed APIs. Text-to-speech synthesizes the response audio. A neural vocoder like Hi-Fi GAN converts a Mel Spectrogram to natural speech. VAD plus wake word, less than 15 milliseconds. ASR, streaming, less than 200 milliseconds. NLU plus dialogue, less than 120 milliseconds. TTS first chunk, less than 150 milliseconds. Total target, less than 500 milliseconds. The total round trip, from the user stopping speaking to the first audio response, must stay under 500 milliseconds. Streaming ASR and chunked TTS are essential to hit this. The feature extraction row converts physics to mathematics. Waveform, framing, Fourier transform, Mel filterbank, log spectrogram. The model row converts mathematics to meaning. Conformer encoder, decoder, transcript, natural language understanding, and speech synthesis. Log Mel spectrogram, 2D perceptual audio fingerprint. Transformer, global self-attention across all frames. Conformer, attention plus local 1D convolution. CTC, fast, frame independent, needs ext. LM. Transducer, streaming, auto-regressive, industry standard. If this video helped you understand modern speech AI, please hit the like button. It genuinely helps this channel. Subscribe to catch every new explainer as it drops. Share with anyone learning machine learning or AI, and comment to tell me which topic you want covered next. What is attention? The complete mathematics. What is tokenization? BPE, word piece, sentence piece. How embeddings work, words as vectors in geometry. How LLMs generate text, sampling, temperature, beam search. RAG explained visually, retrieval augmented generation. Subscribe now so you do not miss any of them. See you in the next one.